Okay, we are starting Chapter 8. We are looking at solutions. So this chapter is not only going to look at kind of what solutions are, specifically how they form, but also some of the properties of it and dealing with kind of how concentrated a solution is. So that's kind of our plan here. So to begin with, we're actually going to take a step back into Chapter 17, which the very astute among you may have noticed that we skipped. But there's a little bit here that we want to deal with in this process called solvation. And so imagine a glass of water, and the water molecules, they're going to be constantly in motion. Here I say because they're kinetic energy, it's really just they're not at absolute zero, so they're in motion. So the water molecules have kinetic energy, they're in motion, they're moving around. Now if I put a salt crystal in it, sodium chloride, the water molecules, because they're in motion, will collide with the salt crystal. Now, what's going to end up happening is water molecules are polar. And so you remember from our bonding chapter that polar molecules have a positive and a negative end. So the positive end of the water molecule is going to be attracted to the chloride ion because it's negative. The positive the negative end of the water molecule will be attracted to the sodium ion because the sodium ion is positive. And so they attract each other. And as they attract, the water molecules actually end up surrounding these ions and pulling them apart from the crystal themselves, so that you end up, and I have a picture of this on the next slide, with these ions, positive or negative, sodium or chloride, surrounded by these water molecules, just pulled away. And that's how something dissolves. That's how a sodium chloride or salt crystal dissolves. That's how anything dissolves, is think of in this case, the water kind of pulling off, attracting and pulling off those individual particles, surrounding them, and then just isolating them. And we call this process solvation. Solvation is just the fancy word for something dissolving. And so we can see here, so this big chunk in the middle is our salt crystal. We can see we have negative ions, we have positive ions. And then we have the water molecules, and the water molecules, again represented by these little Mickey Mouse shaped things here, have a negative end, they have a positive end, and they're going to be attracted. So here, negative end, here, positive end. So they attract, and then we see the picture on the right. So here, that would be like that chloride ion being surrounded by the water molecules being carried away. Here you have that sodium ion surrounded by water molecules being carried away. This is how something dissolves. That crystal is going to get smaller over time. That's what we see. We don't actually see the individual ions. So that's why it appears like if you put salt in water that it dissolves, or put sugar in water, it disappears. It's dissolving. It's still there. It's just surrounded. Those individual molecules or ions are surrounded by these water molecules. Here's kind of another look at this. So if we zoomed in, so on the left we have that sodium ion. Should be much, much smaller than that chloride. Bad image, I stole this from the internet on. But we can see the negative end of the water molecules kind of surrounding and attach that sodium. On the chloride it's the opposite, because the chloride's negative, the positive end of the water molecules are surrounding it. Now, with some ionic compounds, the attractions between the ions and the crystals are stronger than the attraction exerted by the water. So the water molecules are exerting a force. They're trying to pull those ions apart. But in some ionic compounds, the attractions between the ions and themselves are stronger than the attraction of the water. And in this case, it won't dissolve. So we call those substances insoluble. So that's what's happening if you put something in water and it doesn't dissolve or won't dissolve, is the attractions within that substance are stronger than the attractions to the water. So they just don't work. The general rule, and this is kind of summarized with the term like dissolves like. Generally, a polar compound, like water, will be able to dissolve ionic and polar compounds. So that's why water can dissolve salt. Salt is ionic. It's why it can dissolve sugar. Sugar is polar. Non-polar solvents will dissolve non-polar compounds. So again, that's why it's like dissolves like. Okay, now we're into 18.1, so we're looking at solutions. So, first off, our definition that we're going to work with a solution, it's a homogeneous mixture. We're always talking homogeneous mixtures. That means it's uniform throughout, but I want to note it's a mixture, not a substance. So we're not talking compounds here. We're not talking chemical bonds acting between these. We're talking just physical mixtures. And solutions can be grouped up based upon the physical states. So, a couple terms we want to be careful of. So there's the term solute and the term solvent. The solute is what is being dissolved. The solvent is what is doing the dissolving. So in the previous example where we had salt dissolving in water, water would be the solvent and salt would be the solute. It's very important to keep those two separate. Now, let's talk how fast things dissolve. So if I place a salt crystal in a flask, it will eventually dissolve. But what can I do to change the rate at which it dissolves? Well, if you shake this or stir it, it will dissolve faster, which is why, like when people put sugar in their coffee, they stir it up. And that's because that's going to increase the rate of the solution or solvation. And the way that this works is because if you kind of imagine that picture that we saw with the salt ions being surrounded by the water molecules, is that when you stir it, you bring water molecules that are not currently attached to any of the ions into contact with the salt. So you're bringing kind of fresh solvent into contact with the solute, and that allows it to dissolve more quickly. But what's important to note is that stirring, so stirring, shaking, or agitation affects the rate at which the solute dissolves, not how much. So one of the things we're going to see is that there's a limit to how much of different things you can dissolve in a certain amount of solvent. And stirring doesn't change that. Stirring just changes the rate at which it dissolves. Temperature also plays a major role looking at the rate at which solute dissolves. And as a note, it also affects how much it can dissolve. So this one can actually change not only the rate, but the amount that can be dissolved. And again, generally, if we want something to dissolve faster, we want to bring solvent into contact with the solute as quickly as possible. If you have warmer solvent, its particles are moving faster. They have greater kinetic energy. They're moving faster. And because they're moving faster, they're going to kind of hit that solute more frequently. And so there's more collisions. More collisions means that the water molecules can be attracted to the ions sooner, which means a greater rate of dissolving. Last one is particle size, also plays a role. And we talked about particle size in terms of reaction rates way back in, I think, chapter 2. But what we find is that the finer you chop something up, the smaller the particle size becomes, the more surface area you get. And the more surface area you have, the more solute that is exposed to the solvent. Again, the faster we can get the solvent into contact with solute, the faster this will dissolve. So having smaller particles kind of switches things around. So now we just have more solute visible. And so the solvent can pull it away, solvate it much faster. So smaller particles have a much greater rate of dissolution. And we kind of see this here in terms of surface area. So if I have a crystal, has a width of 1, it's 1 particle, it would have a surface area of 6. This middle one here, if I chop it up now, so there's now 27 particles and it has a surface area of 18 because you still have the surface that was exposed on the outside, but now you have all this interior as well. So we've exposed new surface. And the finer you chop something up, as we can see with the picture on the right, the more surface area that we see. Okay, so when we talk solubility, we're talking how much can be dissolved in a certain amount. So a little bit of a story here. So let's say we start with 36 grams of salt. We put that in 100 grams of water. Water's at 25 degrees Celsius, about room temperature. All of that salt will dissolve. We stir and stir and stir and stir and stir. It all dissolves. We're happy. Now, we add 1 more gram of salt, and we stir and stir and stir and stir and stir and stir and stir. It turns out only 0.2 grams of that last bit will dissolve. The rest of it just stubbornly stays undissolved. Just kind of floats around in the water, mocking us with its undissolvedness. Now, what's happening with that last 0.8 grams that will not dissolve? So kinetic theory tells us that the water molecules are in constant motion. Again, we're not at 0 Kelvin, therefore we're constantly moving. That means the water molecules are constantly bombarding the salt crystals, and they're removing and solvating the ions. So if this was all that was happening, we would expect all of the ions will be bombarded by solvent and all of it will eventually dissolve. But that's obviously not what's happening, because we have 0.8 grams that won't dissolve. So this tells us there's something more, there's something else that's going on. So what is that something else? That something else is we actually get an exchange. Is that what ends up happening is naturally that some of the solvated ions, that means the ions surrounded by the water molecules, will recollide with each other, even surrounded by the water, and they'll stick together. And so the water will kind of drop them, and they will undissolve. And the more particles that we have that are dissolved, the greater the rate that this happens. So yes, new water molecules are hitting the undissolved salt, the solid is solvating, and they're being dissolved. But at the same time, we reach this point that an equal number of particles are undissolving. That means they're coming out of the solution. They are going back to the crystal form. So we are dissolving and undissolving at the same time. And so eventually we hit this point that when you're dissolving and undissolving at the same rate, at the same time, that the amount that's undissolved remains the same. But the particles that are dissolved and undissolved are constantly changing. So that salt, 0.8 grams of salt, will constantly be changing shape, because which particles are dissolved, which are undissolved, constantly changing. But the fact that you would have 0.8 grams undissolved at all times, that stays the same. So that's what's happening when we can't dissolve anything more. By the way, this is called a dynamic equilibrium. Think of equilibrium being kind of like being in balance, and dynamic means changing. So we are changing who's dissolved, we are changing who's undissolved, but it's become this balancing act. Now, once we get that dynamic equilibrium between a solution and the solute, that means that we're dissolving at the same rate that we're undissolving, you get what's called a saturated solution. Now, what is a saturated solution, I hear you asking? A saturated solution is a solution that will contain the maximum amount of solute for the amount of solvent we have at some temperature. Now, those of you who are particularly astute may notice that there's kind of two qualifiers on here, for a given amount of solvent and for a certain temperature. So we change those, we can actually change whether or not a solution is saturated or not. We call the solubility of a substance the amount of that substance that can be dissolved, so it's always based on the solute, that can be dissolved in a given quantity of solvent at a given temperature in order to produce a saturated solution. So for instance, with the salt example we were just looking at, we could have 32, was it 32 or 30.2, I think, grams of salt dissolved in 100 grams of water at 25 degrees Celsius. That would be the solubility of salt. In your notebooks, if you're actually in my classes, you will find that I've provided you with some solubility values at different temperatures for water. And what you're often going to see is how many grams of solute you can dissolve per 100 grams of solvent. Any solution that contains less solute than the saturated amount is called unsaturated. So we have saturated, that means we're at that dynamic equilibrium, that means we have the maximum amount dissolved. We have unsaturated, which is has less than that amount. And just for a little bit more vocabulary, if you have two liquids that can be dissolved in each other, they are called miscible. So for example, alcohol and water are miscible. We can dissolve alcohol in water, we can dissolve water in alcohol. Liquids that are not soluble, in other words, insoluble in one another, are called immiscible. So oil and water would be an example of that. So what affects solubility? That's what we're going to look at next. For most substances, solubility goes up as temperature goes up. Pretty simple. But for some things, mostly gases, the opposite is true. There's a table in your book, also in your notebook, listing of common solubilities. You don't have to memorize it, just providing it to you for work purposes. And again, what we find is the solubilities of gases are actually the opposite. For gases, generally as temperature goes up, the solubility goes down. And if you've ever seen, like, had a glass of water sit out where it warms up a little bit, or you just, even when you start to heat up water, you see bubbles forming before it boils, that's actually dissolved gases, or gases that were dissolved undissolving, because you've increased the temperature, so they're less soluble, so they're going to undissolve, and that's what those bubbles actually are gases that were dissolved, like oxygen, nitrogen, carbon dioxide, that were dissolved in the water that are undissolving. Okay, we're going to walk through kind of an example problem dealing with solubility, the type you might see on an opportunity or something like that. So how many grams of sugar, sucrose, can be dissolved in 1,000 grams of 50-degree water? So first thing we do is we look up the solubility of sucrose in water at 50 degrees Celsius. And we find that that's 260.4. Now what that is, it's 260.4 grams of sucrose per 1,000 grams of water. So at this point, it's really just unit conversion time. So we start with what we're given. We'll start with that 1,000 grams of water. And the solubility becomes a unit conversion, a conversion factor. So we see this top number here. This is the solubility that we found, and it's always over 100 grams of water. So if you're doing these problems, it's pretty simple. You can simply just start with the mass of the water, multiply it by whatever the solubility is, and that bottom number there will always be 100. So pretty straightforward. Okay, pressure affects solubility, primarily with gases. So what we find is as we increase the pressure on a solution, the solubility of gases increases. This is actually why when you open up a soda, you get that psht noise when you first open it. It's because they want as much carbon dioxide dissolved in that solution as possible. And to maximize the amount of carbon dioxide that can be dissolved, that's what gives it that fizziness, they bottle it at really high pressure. And when you open it up, the pressure drops, the carbon dioxide undissolves and starts escaping, and that's some of why you get those bubbles forming, why it can fizz out, things like that. So yeah. And if you leave a drink out, it will continue to undissolve, because now you're at just atmospheric pressure, the carbon dioxide will undissolve, and you end up with a flat soda. Interestingly, they actually sell things for 2-liter bottles called fizz keepers, and they attach the top of your 2-liter bottle, so when you've poured your drink, you actually pump it full of air again, increasing the pressure, increasing the solubility, so it's supposed to help your 2-liter bottle stay fizzy longer. So Henry's law is the mathematical relationship of what we were just talking about, the relationship between solubility and pressure. So Henry's law states that at a given temperature, the solubility of a gas in a liquid, solubility here given by this S, is directly proportional to the pressure above the liquid, so the P. So directly proportional, just to remind you, that means as one goes up, the other goes up. So again, higher pressure, higher solubility. And solubility here will usually be grams per liter or grams per 100 grams of solvent. Doesn't really matter as long as you're consistent about it. And mathematically, Henry's law is seen as this. So S1 is the initial solubility of that solution, or of that gas. And P1 is the initial pressure. So we'd say at some, this pressure, this is the solubility. S2 is the new solubility, almost always what we're solving for. P2 is the new pressure. Sometimes you're solving for that. So you do have a little bit of algebra you have to do here. You will generally be solving for either S2 or P2. So we're going to walk through an example of this. So a certain gas has a solubility of 0.16 grams per liter at 104 kPa of pressure. kPa is just a pressure unit. Don't be too concerned about that. If you see ATM, that's a pressure unit. You see torr, T-O-R-R, that's a pressure unit. If they say something of pressure and it's a weird set of symbols, it's just a pressure unit. So we want to know what the solubility is when the pressure is raised to 288 kPa. So I start off with Henry's law. It's talking solubility, it's talking pressure. So S1 is the initial solubility, which is that 0.16. P1 is the initial pressure, that 104. What is the solubility when the pressure is raised to 288? So that 288 is the new pressure, the P2. So in this case, we're solving for the S2. So I do a bit of algebra magic. I multiply 0.16 by 288, divide by 104, so cross multiply and divide, and I get a solubility of 0.44 grams per liter, which should make sense, because as pressure goes up, solubility goes up. Pressure went up, solubility went from 0.16 to 0.44. So supersaturation is kind of interesting. Supersaturation is a really finicky thing. Supersaturation is where you end up with more solute dissolved than you should be able to. So here's how this works. So generally, if you have a saturated solution with excess, so that means you have a saturated solution with undissolved solid there, and you heat up the solution, you raise the solubility, the excess will dissolve eventually, maybe making a new saturated solution at a higher temperature. If you then slowly, gently, carefully allow it to cool, the solution kind of forgets how to undissolve. It kind of lacks a pattern to base the dissolution off of. So if you slowly cool it down, it's not going to crystallize. In other words, the solute that should undissolve won't. We call this solution, which now has more dissolved in it than it should, a supersaturated solution. If any of you have ever made candy or fudge, this is how this is done. Is you take sugar, add it to water. It's a lot of sugar, add it to water, and you heat it up. Then you slowly cool it down. You can't stir, you can't shake, you can't even have scratches in your container. But if you do it carefully, you end up with this cool solution that has way more sugar dissolved in it than it should be able to. And we call that a supersaturated solution. There is no dynamic equilibrium like there is with a saturated solution, because there can be no undissolved solid. If you've ever had fudge, for instance, that tasted grainy, that's actually the result of someone breaking this supersaturated solution. Really easy to have happen, where there's a scratch in the pan, and as you cool it down, the sugar undissolves. Or even a single grain of sugar that was like sticking to the side of the pan falls in, all the excess undissolves. Now, if you do happen to add an undissolved solid to the supersaturated solution, it's called adding a seed crystal. All that solute that should have been dissolved that hadn't will very rapidly solidify, kind of bonding to the surface of the seed crystal, and so you again breaks your supersaturated solution. It's a tragedy. Okay, section 18.2. This is a very mathy section. This is looking at different concentration units. It's ways to talk about how concentrate or how much solute we have for some amount of solvent. So again, concentration just tells us how much solute there is that is dissolved in a given amount of solvent. There's qualitative terms, concentrated or dilute. Concentrated means high concentration, dilute means low concentration. We're not going to be using those overly much because they have no math, and we like math. We do like math. And that's what we talk about there. So, just like the most important unit in chemistry is the mole, the most important unit of concentration is molarity. Molarity is the standard unit of concentration that we use, abbreviated with a capital M. And what molarity is, it's the number of moles dissolved per 1 liter of solution. I want to stress the parts of this. How many moles of solute per 1 liter of solution? So if I tell you that, and molarity can often be abbreviated as molar, so if I tell you you have a 5 molar solution, that means you have 5 moles of solute per 1 liter of solution. If you have a 0.1 molar solution, that means you have 0.1 moles of solute for every liter of solution. What this is really going to come into play, just like we used moles as like in the mole-to-mole ratio in our stoichiometry, we're going to use molarity as moles per liter. So that's where, if you are given molarity, that is how many moles per liter. It's also known as the molar concentration. Now, one thing I want to stress, this is moles per liter of solution, not liter of solute, because adding the solute can actually change the volume of the solution. So we're looking at the solution as a whole. To find molarity itself, so if I ask you to find molarity, it's pretty simple. Molarity is simple, moles of solute per liters of solution. When you divide these, that will break it down to that many moles of solute for every 1 liter of solution. Sometimes problems are mean. They don't give you moles of solute. Sometimes they give you grams. So what do? Well, you turn grams into moles. So let's look at an example of this. All the work's here already, so let's kind of just go through this. So we have a saltwater solution. Saline solution contains 0.90 grams of salt per 100 milliliters of solution. What's its molarity? Well, molarity requires moles and liters. We don't have either. So first thing I need to do is turn this 0.90 grams of salt into moles. So 0.90 grams of salt. I'm dividing by the molar mass. That's how I turn moles into liters, giving me 0.015 moles of salt. Finally, we now have moles. Now, liters are interesting. We don't actually have liters. We have milliliters. And it turns out the easiest way to convert milliliters into liters is simply tack on times 10 to the negative third to that volume. So 100 milliliters becomes 100 times 10 to the negative third liters. So I have my moles, I have my liters, I divide, and I get my answer. So that's a 0.15 molar solution. I will guarantee you questions like this. You must be able to do this. So making dilutions. So once we have a solution, we don't always want it at the concentration that we make it at. We might want other concentrations. So, for instance, when I buy chemicals from a chemical supply company, they come in known, usually high concentrations. But we need to be able to dilute it to safe amounts. So for instance, when I buy hydrochloric acid, which is a pretty strong, nasty acid, I buy 12 molar hydrochloric acid. I want to be able to dilute it down to safe amounts so that we can use it in labs without great risks. So this is how we do it. We make a solution less concentrated, we dilute it by adding more solvent. That's the easiest way. Add more solvent makes it more dilute, because remember, molarity is moles of solute per liter of solution. If you add solvent, the moles of solute are staying the same, but you're increasing the volume of the solution. So you're increasing that bottom number, lowering the overall molarity. And that's what that says right there. Now, if you rearrange the molarity equation, you are not responsible for knowing how this happens. I'm just showing you because I think it's kind of neat. You find that moles of solute equals molarity times liters of solution. So that's me multiplying both sides by liters of solution. Now again, when you make a dilution, the moles of solute remain the same. So we could say that moles of solute equals some initial molarity times some initial volume. But because the moles are the same, that's a constant, we could also say some new molarity times some new volume. So this here, M1V1 equals M2V2, becomes what is called our dilution equation. And again, M1, the initial molarity, that's usually the high concentration. It's called the stock solution. V1 is the volume of that initial stock solution that we're using, that we're starting with. M2 is the new desired molarity, V2 being the new desired volume. So let's look at an example. So the question is, how would you prepare 100 milliliters of 0.4 molar magnesium sulfate from a stock solution of 2 molar magnesium sulfate? Again, all the pieces here are shown. I'm not sure what happened to my animation. So first we wonder, what are we solving for? Well, when it says, how would you prepare, what we're pretty much always solving for is that V1. Is how much of the stock solution are we needing to start with? So I take the M1V1 equals M2V2. I rearrange it to solve for V1, giving me this. And finally, it's just a plug and chug. The new molarity is at 0.4, so 0.4. The new volume is 100 milliliters, V2. And the initial concentration, the 2 molar, 2 molar. So you multiply, you divide, and you get your answer. You get your V1, which is almost always what you're solving for. That's telling us how much stock solution we need to start with, and then we dilute it to the target volume that we want. Percent solutions. Percent solution is a concentration unit that is done very kind of non-chemistry based, very commercially common. And where this comes in is really helpful if both your solute and solvent are liquids. We can do a percent by volume. And all it is you take the volume of your solute, divide it by the volume of the solution, multiply by 100%. Simplest thing you can do. When you're doing this, you want to label your unit as percent V/V. That tells us it's percentage, and it's based on the volume. Now you can do a percentage when you have solids and liquids. So you can do a mass to volume as well. And mass is actually pretty easy. This is a pretty simple one to do experimentally because mass is easy to find. You stick your solute, put it on a weighing tray, put it on a scale, you get your mass. Then you find the volume of your solution, stick it in a graduated cylinder, bam, there you go. So it's just the mass of the solute divided by the solution volume, and then times 100%. And again, the units here, grams per milliliter, because you have grams, you have milliliters, and it's a percentage because it's a percentage. So an example problem, what's the percent by volume of ethanol in the final solution when 75 milliliters of ethanol is diluted to a volume of 250 milliliters with water? So we want the percent by volume, so we take the volume of the solute, 75, divide by the volume of the solution, 250, times 100. That's it. That's all it is. Another example using the mass. So how many grams of glucose? So now we're going to work backwards here. So this is interesting. How many grams of glucose would you need to prepare 2 liters of a 2% glucose solution? So this would be commonly done in like hospitals if people have a glucose feed and they need to have a certain percentage. So the trick is this percentage and what this percentage means. By saying you have a 2% solution, that means you have 2 grams of glucose for every 100 milliliters of your solution. That's what the percent means. 2 grams per 100 milliliters. So it's really just unit conversions. So I start with my unit conversion here, just kind of putting it there, 2 grams of glucose per 100 milliliters of solution. I'm turning the milliliters into liters, so I multiply here. So cross cancel the milliliters, I'm now in liters. Why do I want to be in liters? Because we're told we have 2 liters of solution. So 2 liters, and I get my answer. You could see problems like this. And again, you're working backwards using what the percent means. So now we're going to look at the colligative properties of solutions. This is a non-math section. Section 4 is the math behind this, so just keep that in mind. So what we know is that the physical properties of a solution are different from those of the pure solvent, and not just because we've added solute. Well, so it's not like salt water is different than water because it tastes salty. There's more to it than that. A colligative property is something that changes based on the number of particles you have dissolved. So a colligative property changes as you add more salt to salt water. What are these colligative properties? The big ones that we're going to focus on, and there are more, but these are the ones we're going to look at, are boiling point elevation and freezing point depression. Now, a note about colligative properties. Again, all colligative properties are based, they are proportional to the number of particles the solute makes. It doesn't matter what the solute is. It's purely how many particles we have. So for instance, sodium chloride, when I dissolve it in water, because it's ionic, breaks up into sodium ions and chloride ions. So that means for every 1 mole of sodium chloride, we actually get 2 moles of particles. Now, this is important because glucose is a molecular compound, so it doesn't break apart at all. So for every 1 mole of glucose, I get 1 mole of glucose molecules. So if I have one solution that's 1 molar sodium chloride and 1 molar glucose, the sodium chloride one would have greater colligative property effects. It would have twice as much because it has 2 moles of particles instead of 1. And that's the idea behind here. So first, boiling point elevation. So this is all about attractive forces. So at the beginning of this chapter, we talked about that when you have a solute, it's attracted to the solvent, and the solvent is attracted to the solute, and the solute is surrounded by the solvent. So there's attractive forces. So when you're trying to boil something, there's more attractive forces if there's a solute present. And to boil, you need to break apart all these attractive forces. So it takes more energy. It requires a higher temperature to overcome these additional attractive forces that are keeping it in the liquid state. So the net effect is that the boiling point goes up. Now, what is boiling point? And this is where the top part just appeared. The boiling point is the temperature at which the vapor pressure of the liquid phase equals the atmospheric pressure. So that's, you might just think the boiling point is the temperature at which something boils. True, but what is boiling? Boiling happens. It happens when the vapor pressure, that is the pressure, so everything has a vapor pressure because just randomly pieces of it can get enough energy to vaporize, and that gives us a vapor pressure. When the vapor pressure equals the atmospheric pressure, that's the pressure in the air around it, it's now going to start boiling. When you raise the temperature of something, the vapor pressure goes up. That's why at a certain temperature, vapor pressure equals the atmospheric pressure, and it boils. Now, if you have a solution, you're increasing the amount of attractive forces. You're increasing how much energy is needed for this to vaporize. In other words, you're making it harder. Freezing point depression is kind of the opposite. So remember, when a substance freezes, the particles kind of take on this orderly pattern. Solutes disrupt that orderly pattern. They get in the way. It's kind of like, imagine a couple in the hallway is about to embrace, and right before they embrace, you jump in between them. It's going to make it harder for them to get close together because you're in the way. That's what the solute does. So you have to take even more kinetic energy away. You have to cool it down even more in order for a solution to solidify. So the net effect of this is when you have a solute, and the more solute there is, the higher the freezing, or the higher the boiling point becomes. In other words, becomes harder to boil, and the lower the freezing point goes, makes it harder to freeze. This is why we salt roads in the winter. We're adding salt. We're adding salt to water. What ends up happening is we add enough salt to lower the freezing point enough that the temperature that we're at, that saltwater solution now will not be frozen. We've lowered the freezing point. This is why we add antifreeze to the coolant in your radiator. Because if you just had water in your car's radiator, that water hits 100 degrees Celsius, it boils. You add antifreeze to it, you're adding a solute. It raises the boiling point, so that can now be at a higher temperature than 100 without boiling, and that's good. Okay, last section. So this is the calculations involved with colligative properties. So not just enough to say boiling point goes up, freezing point goes down. We want to know how much that will be. So again, colligative properties depend on the number of solute particles. The greater that ratio becomes, the greater the ratio solute to solvent, the greater the colligative property effect is. So, to do this, we use a new unit called molality. Molality, not molarity, molality. And molality is given by a lowercase m, as opposed to molarity, which is an uppercase m. I think they did this just on purpose to confuse you. What molality is the moles of solute, so this top part's the same as molarity, but instead of 1 liter of solution, it's 1 kilogram of solvent. Now, why do we do this? Why don't we use molarity when talking colligative properties? Well, because molarity is based per liter of solution, and when you change temperatures, the volume changes. So that means your molarity actually changes as you change temperature, and that's bad. But molality is moles of solute, kilograms of solvent. That remains constant as temperature changes. So this is why we use this when dealing with boiling point elevation and freezing point depression. This here is your equation. Now, sometimes I want to throw this out there. You will see the mass is given in terms of grams. So you probably want to be in kilograms because, again, kilograms of solvent. So be careful with that. Again, not the same as molarity, just an unfortunately similar name. So let's look at a calculation with molality. How many grams of potassium iodide must you dissolve in 500 grams of water to produce a 0.06 molal solution? So instead of a molar solution like molarity, it's a molal solution. So again, they kind of gave us a hint. They said 0.060 molal solution. That means we have 0.060 moles of potassium iodide per 1 kilogram of water. So again, that's what that says there. So we can start with the 500 grams of water. And again, 0.060 moles of potassium iodide. That's the molality per 1,000 grams because, well, there we're working in grams, and 1,000 grams is every kilogram. We could have started per 1 kilogram and turned the kilograms to grams, then did the cancel out the grams of water. But regardless, that gives us moles, but we don't want moles. We want grams, so then I do molar mass here. So we can see, cancel out the moles, grams, we get our answer. Okay, calculating this. Again, we know the boiling points and the freezing points are different. How do we find this? So the change in the boiling point, delta T sub B. Delta means change. T sub B is boiling point, boiling temperature. So we're looking at the change in the boiling point. In this equation, you're going to see a lowercase m. That is the molality of the solution. Then you'll see this factor. It's the n factor. I've called it the I factor. Different books call it different things. That's how many particles each molecule or formula unit breaks up into. If it's a molecule, that I or n value will be 1. If it's ionic, it's equal to the number of ions present. So if it was sodium chloride, NaCl, that would be an I or an N value of 2, for instance, 1 sodium and 1 chloride. If it was something like aluminum, oh, that's terrible, chloride, and let's say we got that to dissolve, that would have an N or an I value of 4, 1 aluminum and 3 chlorines. Finally, you have K sub B. K sub B is called the molal boiling point elevation constant. I will just call it K sub B. That is given to you in your textbook. Don't memorize those values. They'd be provided to you in the problem. So an example. So what is the boiling point of a solution that contains 1.20 moles of sodium chloride and 800 grams of water? So our equation is this. So I'm skipping around a little. Delta T sub B equals K sub B times m, so K sub B, m, and then the I, that's that I value, that's how many particles it breaks up into. So K sub B is given to us, is 0.512. The I is how many particles it breaks up into. So sodium chloride is ionic, sodium ion, chloride ion, I value of 2. So what we need is the molality. And molality is moles per kilogram of water. So we were told we had 1.20 moles. We were told 800 grams of water. That's 0.8 kilograms. So this gives me a 1.50 molal solution. So I plug in 1.50. So what this gives me is it tells me that the boiling point change is 1.54. You are responsible for knowing the boiling point of water is 100 degrees Celsius. Boiling point goes up, boiling point elevation. So new boiling point 101.54, because 100 plus 1.54 is 101.54. Freezing point depression works pretty much the exact same way. The only difference is instead of B's, it's F's for freezing. The K sub F is different than the K sub B, by the way. And again, that is basically the exact same thing, but again, freezing point goes down, so you find the freezing point of your solvent. You are responsible for knowing that the freezing point of water is 0, and then we subtract this from that. Finally, we can actually use these colligative properties to help us find the molar mass of an unknown compound. Pretty neat. So I'm just going to walk through an example of this. So here's the information. A solution of 0.750 grams of a non-volatile molecular compound. So non-volatile just means we don't have to worry about any other pressures. It's not reacting. Molecular compound is telling us that the I value equals 1. We're given a mass of water. We're given the new boiling point. And here's our pressure. Don't really need to worry about that. What's the molar mass of the solute? So first thing we're going to do is calculate molality. So I know that the delta T sub B is 0.78 because we were told this is the new boiling point, 100.78. We know that the original boiling point of water is 100, so the delta T sub B is 0.78. So we're kind of working backwards here. So we're starting with that delta T sub B equals K sub B times M times I, and we're using that to solve for molality. We find the K sub B of water is 0.512. We looked that up in the book. The I, or the N, was 1. So we know this, we know this, we know this. We can solve for molality, and the molality is 1.5. So the molality is 1.5 moles of solute per kilogram of water. That's our first step. Next, we know that we have 1.5 moles of solute per every 1 kilogram of water. So I turn my kilograms of water into grams. And we were told we had 22.6 grams of water. So grams of water cancel, so we're left with moles of solute. So we've now found we have 0.34 moles of solute. Remember, what is molar mass? Molar mass is grams per mole. We now have our moles. We were told in the problem that we had a certain mass of the solute that was added. We just take that mass, divide it by the moles, we get our answer.